review the program. The next presenter is Uriel Alberto Lopez Islas. He's a PhD student from Instituto Tecnológico de Tijuana. He's going to present the talk, Multi-Target Regression with Genetic Programming. So please welcome Uriel.
The talk is Multi-Target Regression with Genetic Programming. The content we're going to present. We have a quick introduction, a little bit of background. We're still working on this, and we're open to any suggestions or recommendations towards the investigation of this course. So, whenever we want to do a regression learning or classic method, we're highly dependent on the quality of our data set. What do we mean by this? That we are highly dependent on the quality between input and output. The better the relationship between input and output, the better the solutions we'll be able to find through our regression test. For example, top two data sets are kind of easy. We just can see them and we can give it to some algorithm or any method, and we will be able to find it with ease. And this data set, which has both of them, but in this data set, we have classes, we have labels for each one. We know that the red ones are be able to find the solutions with really good accuracy, right? But taking into notice and account this particular data set, if we remove labels and we give this problem or data set to our algorithm to solve, well, the task becomes a little bit more complicated. These kind of problems. When we were searching in the literature for something that looks like this or this, we found that we have the blind source separations, which consists on retrieving a set of unobservable signals or sources from an observed set of mixed ones, and to exemplify party. And we want to hear, and a lot of people are talking, and we really want to hear just one person. By applying blind source separations, what we need is a lot of sensors, meaning that we have like one microphone here, one there, and one there. All of them will have the same information, but some of them will have, for example, if we want to hear what Juliana's talking about with someone, so where we can see example of this is an analysis of biomedical signals, feature extractions, voice-controlled devices, and in summary, to solve this problem, the data is projected onto new axes, and it can use measures of variance to project to a set of orthogonal axes, or it can utilize measures of non-Gaussianity like kurtosis. But all of these methods assume that in any case, we can adapt it and say that we have just one sensor for all the signals, and they don't mix. All the signals come in as they are and don't mix between them. They don't add up. So that's sort of how we can see it if we try to apply it or look at it as a blind signal separation, but it is not. Okay, moving on from this, we found the multi-task regression problem. But to talk about this, let's talk about, again, the simple or traditional way to do a regression problem. In a traditional regression problem, we have a matrix of inputs and one vector of outputs. And in a regression task, we have to find a function which maps our x to our y's. That's the most regression takes a matrix of inputs and a matrix of outputs. But we know exactly that all of this map onto all of this, and one row of the vector of the one column of the matrix of outputs, and the same inputs map to another one and another one. So we know exactly how many sources we have to find, and we know exactly how they map to, where they go to. Okay, so the formal or a definition we're checking from literature: multi-targetable simultaneously, or the task of predicting multiple continuous variables using a common set of input variables.
And we can formally define multi-target regression as an input space of X with tuples of dimension D containing primitive data types. For example, for each xi and x, we have these samples, right? An output target space Y with tuples of dimension T. This is really important. Containing real values. And we know that these go from 1 to where each example is a pair of tuples from the input and the output space. So it's just a sample from the previous ones. And we have a quality criterion, which rewards models with high predictivity, accuracy, and low complexity. And we have to find a function which maps X to Y, such that F maximizes the quality criterion. So how does our problem differentiate from the traditional multi-target regression task? Well, as we remember, a multi-row, column, and matrix. In our variants of the problem, we only have one output. And I just colored this part because we know that there are at least two signals or two sources in that output vector. But we don't know where which corresponds to which one. So you can imagine this problem by having a lot of sources in one, but we don't know which goes to which. Because if we knew, or we have labels or class labels, we could reconstruct it and create it into a traditional multi-target regression task. But it is not. I don't know if I made it this clear. Okay. So we redefine the problem for our problem as and we only change that we do not know the dimensions of size of the tuples. Some of the elements in Y may be missing in the output tuples, and at least one of the elements in each eth sample. But J is unknown for each sample. We don't know how many outputs we have. Okay. And we have to find, I don't know if this holds, but we try to find a set of functions, not just one, that map the whole input to output. How are we going to solve this problem? Okay, we propose this algorithm, which takes us as input the mixed M size of the consensus set, a threshold value to consider a residual, a part of the consensus set. We initiate our solution set as 0, and sorry for this mistake. And the output it returns the separated data set. So we go to step 1, which is generate a copy of the data set, take a random sample of size M from the copy, generate a model from the minimal sample set with genetic programming, get all the residuals from that model consensus set with all the fitness which are lower than the threshold we defined. If the length of the consensus set is greater or equal to the minimal sample set, then we store that model on the solution set, and we subtract the consensus set from the copy. We will repeat steps 2 to 6 until the size of the copy of the data set is equal to 0, and we return all of the points. Then what we require to take a sample, then we delete everything and go to step 1 again. And so it's an iterative process. So how will our algorithm solve this problem? Well, we first take a sample, a random sample. We give these samples to GP for it to construct a model, threshold. And now, all of the values that are within the defined threshold are summarized or counted. Yes. And if the amount of them is greater than the consensus set, we say that we find a solution. But here it's not sufficient, so we skip this sample. And we repeat this, taking samples until we are greater than the consensus set, then we consider it a solution. And we store that model, and we delete all of these points from the data set. And then we redo the sampling, we do all the process, and take this until we have none points to be fitted. When we get to this, we say that we find the solution and but not mixed. I don't know if I'm making myself clear. We gave it to our GP variant, and it's gonna be doing all this process until it finds all the data sets, all the functions. Then we test them, and we get all the outputs that our model gave. These are the problems that we're using. They're all synthetic. And we're gonna solve this type of problems, right? Where we have two data sets, and we take the same data sets and we separate them by 0.5 magnitudes. The point of this is to make them come close together until they're completely overlapping. So these are the types of problems we're going to be solving. The parameterization for our RANSAC GP, because it's what we used, but just differently. We define a consensus set with more complicated data sets. So from each data set, we have at least 100 finished cases per problem in one data set. We are separating them by 1, 0.5, and 0 magnitudes on the range of y. And this is our solutions. As you can see, when we have two data sets which are separated by 1 magnitude, we define a threshold of 0.1 sample set of 20 points. We're able to find with great precision the two data sets. Now we make them come closer. We need to tighten the threshold. So from 0.1 we went to 0.05, and we were able to find the data sets, right? And finally we got to this part where we have no separation. They're completely over. Why did we lower this consensus set? Because some of the points may be taken from the other points. So if we left this value to 100, we will never finish the problem, because each model will take more points from the other point, and we'll never finish searching for that. And now finally, this is the most impressive one, where we have all of the points. I already told you how many they are, but if I didn't told you and I asked you how many points we have here, well, it will be ambiguous, right? And which one goes to which, it's more complicated. So with our algorithm, if we define a really tight threshold of 0.001, the consensus set, the reboot, which is, and our minimal sample set of 20, we're able to find all of the models with great precision. Most complicated to find. I'll talk about it in a little while. And why did I show you the threshold? Well, because if we define a really big threshold or don't readjust the minimal sample set, we can find this type of solutions where we find more models than what are really in the data set. For example, I don't know if you can make out, but here we have an extra model which follows one of them, but it's not a real one. So we need to tighten really good to finalize. The proposed algorithm is able to solve up to 5 benchmarks in one data set, even when we do not know how many models there are. And what I mean by this is we don't tell the algorithm how many models we have. The algorithm can greatly increase results by combining it with local search. That's what I meant with this problem. Because this problem, it was really complicated. It wasn't able to find the red line. So when we applied local search, we were able to find this model. So local search helps. This work is being extended to real-world problems such as energy efficiency, cooling and heating. Also, we're doing a study of how many iterations on average it takes to find a solution for a given data set. And finally, we're open to ideas on how to improve.
Have any questions for real?
In the process of when you propose a model after taking a random sample,
Yeah.
And then you get the model, and then you get the threshold lines.
Yeah, you find the threshold.
And then you count how many points got into that area.
Yeah.
You only count the points that you took from the random sample.
You mean?
Yeah.
Like here.
Yeah.
Right? No, we give when we generate a model from a sample, from a random sample. But then that model is compared to all the whole data set. So the whole data set is the residuals or counted with this model. So that's how we define it, the data set, the whole data set.
Thanks.
Does anyone? Any question? No one? Okay, well, join me to congratulate Uriel and thank you to join us.
Hola, bien, ¿cómo estás? Igualmente. ¿Quién va primero?
Voy hasta el final,
Okay.
pero no sé si tenga que darte en USB o puedo presentar desde
Ahí,
mi máquina.
es que lo presentas desde... Mira, lo estamos copiando todo ahí.
Okay.
Lo que pasa es que de ahí estamos capturando directamente la
entonces
pantalla.
mejor lo paso en un USB y se los paso.
Exacto. Sí, estamos capturando la pantalla.